This is what galaxies look like, galaxies outside our own galaxy. Think about it as if you're looking through a pane of glass and there's a little bit of dust on that glass. The dust are stars in our own galaxy. That means take them away and the rest of the universe is incredibly empty. It has no stars in between galaxies. The galaxies that I chose here are three types. The first one on the left is a spiral galaxy, in the middle is an elliptical galaxy, and on the right, top right, we have an elliptical galaxy side on with a bulge visible. Our galaxy is 100,000 light years, and therefore we zoomed out not quite 100,000 times, but rather more like 1,000 times outwards this time around. Last but not least, let's zoom out by a factor 100, and we know that this is the size of the observable universe. But in that last step, we zoomed out factor 100 rather than 10, and we kind of assumed that the universe is fairly uniform. We have some circumstantial evidence that this is so, but not complete evidence. We will discuss the meaning of that in the next lecture. But now, after we've gone through the universe as we see it, we need to know how we know that. As usual, that is our common question. How did we know that? The hero of finding the structure of the universe from galaxies onwards is a woman by the name of Henrietta Leavitt. She would change astronomy almost as much, if not more than, Tycho Brahe and her fellow Harvard calculators and their boss Wilhelmina Fleming. She was a graduate of Radcliffe College. She transferred to Radcliffe College from Oberlin College, which is a liberal arts college fairly similar to Baker University. After she graduated, she went on to work in the Harvard Calculators group, looking at photographic plates, but rather than looking at spectra like her fellow calculators did, she was told to check on those variable stars, stars that were known to change in intensity but weren't considered very important. She went about it in a brilliant way. First, she found out that the periods were indeed consistent, something assumed but not confirmed before. Then she noted that there were lots of those variable stars in the Large Magellanic Cloud and Small Magellanic Cloud. We know now that these are satellite galaxies of our own, relatively close when compared to Andromeda Galaxy. What she did was to assume that each one is at a constant distance from us, and therefore in each one the variable stars were all at constant distance from us. She then found out that the stars with the longer periods were brighter than the stars with the shorter periods. That's how she established the first and best standard candles that we have to this day. What does a standard candle mean? Assume that there is a light bulb that has some sort of power output, say 60 watt. Assume that on that light bulb it's written in huge letters that it's 60 watt. You see it with the telescope that it's a 60 watt. Then you measure the brightness. So from the brightness you can tell how far the light bulb is. The brighter it is, the closer you are. Of course, if your eye is right next to a 60-watt light bulb, it will burn your retina. If it's a mile away, it will be just a flimsy light. You can go duh, obviously, but as brilliant as they come. Women did not win Nobel Prizes then. So there was not even a conflict like there was with Jocelyn Bell. Neither did male astronomers win Nobel Prizes then, so the next guy that did not win a Nobel Prize, which we will talk about in the next slide, didn't win Nobel Prize either. But there is a fairly famous telescope named after that guy, and none named after Henrietta Leavitt. I think it's time to change that. No, I don't know why her right eye looks as if it was photoshopped, but she did die at age 53 of cancer, not long after she was appointed director of the Astronomical Photography Group at Harvard Smithsonian Center for Astrophysics. This next discovery was made by Edwin Hubble. If you click back and forth, you'll see his picture. Hubble used Leavitt's discoveries for several purposes. We will discuss the second purpose, the second main purpose, next time, but this time around we will discuss the first purpose. First, let me tell you a bit about this fellow. He graduated from the University of Chicago in 1919 after having won the NCAA basketball championship. I'm not joking. He was in the basketball team. For a while, he also was an amateur boxer. For a while, he also was a lawyer. Then he got tired of being a lawyer and became an astronomer, moved to California and worked in Mount Wilson Observatory, at the time the state-of-the-art observatory. In the picture here you see a variable star of the sort that Henrietta Leavitt characterized, but this one is in the outskirts of a nearby galaxy called Messier 100. The three inserts have a star in their middle that changes in brightness periodically. You can see that they were all taken at the outskirts of the galaxy. It was not this specific star that Hubble saw. He saw stars in the Andromeda galaxy first and then in a few other galaxies. But he did use them as standard candles to find how far the galaxies were. Here again is a picture of the Andromeda galaxy that you've seen at the end of the last lecture. And Hubble looked at variable Cepheids in this galaxy to find that it was 2 million light years away. This galaxy is the satellite galaxy in the previous picture, and although Hubble did not find the distance to this specific galaxy, I wanted to show you a picture of it under a filter. This filter only lets very blue light through. The reason I chose to show you that is whereas the previous picture of the stars that you saw there were foreground stars in our own galaxy, in this picture every single dot is a star in that dwarf galaxy. The reason we're seeing it is because this filter blocks all the regular stars. We're only seeing the fat, chubby stars that are still around in that fairly old galaxy. So we're seeing one in many thousands of stars, and only then can we distinguish the fuzz and see actual individual stars in that galaxy. Like that dwarf galaxy, there are other galaxies that are fairly old, and this is one of them that Hubble discovered and found the distance too as well. Notice that the older the galaxy, the redder the tint. As was the case with global clusters, since all of the young ones died out, we're getting to have more of the stars that are reddish, and they give reddish tint to the galaxy as a whole. Here we have several galaxies in the same picture. Some are spiral, like the Andromeda and like our own. Some are old and round, which are called elliptical, and some are kind of bizarre. In this case, and in many other cases, Hubble looked at the shapes and looked at the sizes. Hubble old scheme found that there were several types of galaxies of sizes that were not very different from each other. So, looking at those Cepheid variables, he found out that the galaxies don't come in huge varieties of sizes. The dwarf galaxies that orbit a galaxy like Andromeda may be kinda small, but the rest come at fairly similar sizes. From the E0 that's fairly large, like the one we've seen 2 slides previously, to the spirals, the SA spirals, and then there are the bar galaxies, and you can kinda guess which those are. Kind of SBB would be a very typical one. This scheme of Hubble was used in some of his later models that help us develop the Big Bang Theory. Hubble's scheme for the universe came way earlier than the time in which we had windows into the universe with different wavelengths. In this spiral, I added on top of the visible spectrum a spectrum that comes in the ultraviolet. The reddish tinted areas are areas where lots and lots of stars are being formed. The question is, why would there be such huge amounts along filaments of star creation? Even more interesting is a galaxy of the sort of the one seen here. In the picture on the left, you can see that this looks almost as if there is a wave going outwards and some sort of a wave in the middle. And this is exactly what happened in this case. This is a result of one galaxy splashing into another galaxy, creating a density wave that gives rise to star creation. This used to be called the Tadpole Galaxy, but it's of course a result of two galaxies that collide. They leave behind them a spiral from one and a spiral from the other. As a result of this collision, there is increased regions of star formation. If you recall, where stars are very, very young, the tint is a bit bluish. When they're old, it's a bit reddish. So you can see the filaments and spots where new stars are being born as a result of those galaxies. As a result, we had to update some of those earlier Hubble schemes for how galaxies should be organized. We now think that a lot of the galaxies that you're seeing in these images, this one is from what's called the Hubble Deep Field, named after a region in the night sky where there are very few foreground stars, so that we can see only galaxies. And every picture here is, every point here is a galaxy except for a couple. Now we think that galaxies actually evolve from an earlier fairly weird shape into some that are spiral and some that are elliptical, and some that are somewhat a combination of the two. Hence that tuning fork that Hubble discovered. A fascinating part of how galaxies are has also been very strongly associated with black holes in the centers of these galaxies. In this galaxy, Messier 87, you can see basically a jet coming from a center. That center, which is in the insert on the left, has an accretion disk around a black hole. We don't quite see all the way to the accretion disk, but we see some of the infalling material. This black hole is about 1 billion times more massive than our own Sun, and may be involved in how galaxies were formed in the first place, although this is still a very strong hot topic in astrophysics. We do not know exactly how they're involved. Here are some more details of these jets. These parts of the jet are moving at speeds that are very close to the speed of light. For a while there, those knots seemed as if they were moving at speeds that are higher than the speed of light. Dr. Martin Rees from Cambridge University figured out ways to explain this motion without moving faster than light. Those jets are moving basically at an angle towards us. The little dot in the middle is a galaxy in which in the very center are those jets, and those jets shoot out to distances that are hundreds of times the size of the galaxy. Those lobes that we now call radio lobes come from active galaxies with a black hole in the middle with jets coming out and the radiating in the radio part of the spectrum. Such amazing structures that are so huge are incredibly fascinating, and again, we're still learning about them. One of the things we learn about from those jets is the structure of the very flimsy material in between galaxies. Something else that we're learning from galaxies is about stuff that's behind them. Here's a picture of the Abell cluster, and in that cluster you see arcs. Those arcs are actually not arcs at all. These are galaxies. These are actually galaxies that are behind galaxies in the cluster, about twice the distance, or sometimes even further than twice the distance of those galaxies. Basically, the galaxies here are acting as a lens, kind of like an extragalactic telescope that helps us see even closer to the Big Bang, even further away from ourselves, and helps us also find out how much material is in between us and those incredibly far away galaxies. Here is another example of these extragalactic telescopes. These are called gravitational lenses. Basically, they were predicted by Einstein's gravitational theory, the same theory that explained black holes as we've seen three lectures ago. All of those amazing things that constitute the ingredients of our universe will be taken into account when we're dealing about the past and future of our universe and the Big Bang Theory, which will be the subject of our last lecture. That's gonna be coming up pretty soon.